Hello, I'm Cheng, a PhD student from Hong Kong University of Science and Technology. Today, I will present VBridge, a joint work with MIT, Adobe Research, and Zhejiang University. When a patient goes to a hospital, the hospital stores the patient's electronic health records, including demographics information, diagnosis, lab tests, and treatments. This data can be used to help clinicians predict the patient's future conditions and make decisions like which treatment to take. A typical machine learning-assisted prediction pipeline is like this. The data is stored in a database, and from the database, the engineers in the hospital design and generate features. The features are then input into the machine learning model, and the model outputs predictions like the patient's mortality risk. To help clinician users understand and accept model predictions, a variety of explainable machine learning techniques have been proposed. A group of works focus on designing machine learning models with intrinsic interpretability, such as attention-based neural networks, like retain and retain race. Others provide post-hoc explanation to existing models. For example, rule matrix uses logical rules to explain the model, and the sharp algorithm assigns each feature an importance score, showing its contribution to a prediction. However, there is little understanding of how clinicians expect to use model explanation to support their decision-making. That's what we are going to study in this work. We focus on feature contribution-based approaches, which is one of the most popular explanations for healthcare models. We work with 6 clinicians from a cardiology department at the large children's hospital. We first built a demo model as a design problem that predicts the patient's risk of having complications after the surgery, which is relevant to the clinician's daily work. Then we had one-on-one interviews with them. We showed the participants a sample patient's medical records, features, predictions, and explanations. They will ask several questions, including making their own predictions of the patient. From their feedback, we identified several challenges in explaining machine learning models to clinicians. The first one is that we cannot guarantee that clinicians understand all features, like some statistical values. They may know how to calculate them mathematically, but they do not use them in their daily work. So how should we deal with this problem? Inspired by our previous work, we said clinician users prefer to see related features together. We group these features and show the feature-level contribution to users. For example, features extracted from the same series of medical events are grouped to minimize the information shown to users, and they can check the detailed features only when necessary. Second, clinicians need statistical evidence to support the insights from explanations. We provide designs based on reference values which are calculated from similar patients. We highlight the out-of-reference range feature values with upward or downward arrows. Users can check the distribution of feature values and conduct a what-if analysis to see whether it still makes a large contribution if such a feature is normal. For example, after decreasing the surgical time to the reference range, the model prediction flips and the feature's contribution decreases, indicating that a long surgical time is a reason for the model making this prediction. Third, we found that feature-level explanations are not enough. Clinicians also need the patient's original data as contextual information. To deal with this problem, we first present an overview of the patient's longitudinal health records in matrix-based visualization, where each row shows the records from a common source, such as lab tests and vital signs, and each cell encodes a number of records and the rate of the abnormal test item in time period. Users can inspect details by brushing on timeline view, then the detailed records will be visualized in a temporal view. By default, the system only shows the period when the record values out of the reference range. By aligning them together, users can find critical periods. Users can also check the details of the records by expanding it. We also see strong demand to associate feature-level explanations and patient row records together. We adopt feature tools, where features are defined as functions mapping the medical events to vectors. We then propose several visualization and interaction designs to connect the dots between features and data to expand healthcare models. First, users can select a feature or feature group and query for its related raw data, which are the corresponding records where the features are derived. It can also be done in reverse. For example, if the user wants to find the relevant features to the oxygen saturation records, he can first mark the data and turn on the focus mode to filter and highlight the interesting features. and the related features and data are automatically linked through curves, so users can efficiently check them back and forth. The last function is to highlight influential periods to the relevant features. We apply an occlusion-based method and a dynamic thresholding technique to identify the most influential periods. Let's check our paper for technical details. Then we introduce a use case to show how the system helps clinicians understand model predictions, which also identify their analysis workflows. In this case, the target patient is a 2-month-old infant who was admitted to CSE. The model predicts that he is at high risk of having cardiac complications. A clinician is better to understand the model prediction, which would help him better estimate the patient's conditions in the next few days to make post-operative care plans. After understanding the patient's basic information, he looked at the feature view and noted that the in-surgery features make the most contributions to the prediction, which mainly come from the long surgical time and CBD time. Other feature groups like oxygen saturation, lactate, and pulse also made considerable contributions. To gain a better understanding, he conducted a what-if analysis on the out-of-distribution feature values that predicted them into the reference range. After the system returned the results, he noted that even though the prediction was not flipped, the hatched area indicated that most of the feature contributions significantly reduced. Then he inspected the original records of the interesting features, which are features of the oxygen saturation and lactate. He noted that the oxygen saturation was always below the reference range, while the lactate was at an average level at the beginning, and then began to accumulate. They both indicate that the patient's condition is not good. He then decided to check more contextual information to understand the direct reason for this circumstance. He selected other in-surgery vital signs from the timeline view. He then checked the pulse records. He noticed a drop, which indicated the rescue conducted to the patient, and a period, which was a CPB process when the CPB pump took over the functions of the patient's heart and lungs. Aligning them with the lactate curve together, he saw that the rescue was more likely to be the direct reason. Finally, he was curious about whether the model captured these two abnormal periods. He queried the fine-grained explanations, and he noted that the CPB period is marked in orange, but the rescue time point is missed, which is slightly different from his expectation. But in general, he agreed that the prediction was based on the most potentially critical records and it was trustworthy. He decided to pay more attention to this patient and consider using proactive treatments to avoid the situation getting worse. In the second case, we show a different workflow to use our system. The targeting model predicted that the patient was at high risk of having lung-related complications. First, the user checked the patient's profile and gained an overview of all medical events. Then she selected in-surgery vital signs for details. She marked 4 series of critical records, and among these 4 items, the N2 carbon dioxide records were once below the reference range, which could be a reason causing the patient to have complications. But the other 3 items are quite normal during the surgery. Overall, she saw that the patient's condition was good and predicted that the patient was unlikely to have complications. However, she then found that actually the model made a different prediction. So she referred to the feature view to check the explanations. The feature contributions on the 4 critical items are similar to her expectations. However, some features also have high contributions to the prediction, indicating that she might overlook some factors. An important one caught her eyes. She noted that the red cell distribution's mean value is much higher than the reference range. She then realized that the patients might suffer from anemia, which made her vulnerable to lung infections. After the exploration, the user intended to trust the model prediction and pay more attention to the target patient. In summary, we identify 3 key challenges in explaining machine learning models to clinicians and propose VBridge, a visual analytic system that connects the dots between features and data to explain healthcare models. We also introduced 2 use cases which shows different analysis workflows. Here are some take-home messages. First, clinicians are more familiar with the patient's health data instead of features. Adapting to their workflows, we should provide contextual information and connect the dots between data and features to help them understand the model. Second, evidence-based medicine requires clinicians to use the current best evidence in making decisions. Statistical information from a single group of patients plays an important role in helping clinicians to understand, judge, and accept model explanations. The last one is about model explanations and feature interpretability. Here, we summarize the scope of this research from a technical perspective. We classify the features into three groups. In the first group, features are interpretable to users, such as age, gender, and the average value of the pulse records in the last 24 hours. Most of the existing explainable machine learning works are designed for machine learning models with these features. While in the second group, features are not necessarily interpretable to users but traceable, meaning that we can find a subset of raw data corresponding to the targeted features. Like features generated from automated feature engineering method that derive feature values from a relational database with a sequence of selection and aggregation operations. Our system, VBridge, extends previous work on interpretable features to adapt uninterpretable but traceable features. Well, in the third group, features are neither interpretable nor traceable. Features generated from representation learning methods belong to this category. In this case, the problem is even more challenging since the relationship between features and data is more complex. How to extend the system to support these features remains an open problem. That's all. You can find the code of our project through this link, and thanks for listening.